Today it's all about thermal interface material in power electronics, and here in particular the advantages that flexible foils made of graphite can offer. My name is Erik Rehmann and I'm responsible for marketing at GVA in Mannheim. Our technical presentation today will be given by Bret Trimmer. Bret is Applications Engineering Manager at our partner NeoGraf Solutions in Cleveland, Ohio. He worked for many years in various positions in the semiconductor and electronics industry until he joined NeoGraf in 2010. This webinar is part of our expert series in which we are happy to share our knowledge and that of our partners on new products, technologies and findings from the field on a regular basis. Also, check out our website gva-power.de and register for the webinars that interest you. Or simply visit our YouTube channel and watch the video recordings at a later time. During the live webinar, please feel free to use the chat function of our online portal and ask your questions. We will be happy to address them after the presentation. But now we go live to Bret Trimmer in Cleveland. Bret, thank you so much in advance for getting up so early for us. Can you hear us well?
Yes, I can. Good afternoon.
Good afternoon.
Very good. Let me start the presentation. Very good. Today we'll be talking about flexible graphite thermal interface materials with special emphasis in power electronics. We've been doing this type of material for over 20 years now, and it's become the standard material for several industries, and we'll talk on that. First, a little bit of background. Most power electronics do need a thermal interface material, and these TIMs are used to fill the micro gaps where there is no direct metal-to-metal contact. We recently saw a study where they took a look at two polished plates on top of each other, and they found the actual metal-to-metal contact area was in the order of 3 or 4%. Everything else was an air gap, and as you know, air is a very good insulator, and it really made it difficult for the heat to go from the hot plate to the cold plate. Some customers ask if they can polish the two surfaces to provide perfect contact area. And the answer is yes, you can. It is possible. However, it is very expensive and it's impractical for anything on a commercial basis. So you do need some sort of thermal management material between plates in a power electronics device. Unfortunately, most of these TIMs are chosen based on cost and not on performance or lifetime. And we'll talk about some of the issues that brings up. Most of the time, people will use thermal grease or a phase change material as the thermal interface. These are both fairly inexpensive and they're commonly used. However, both will have several problems. First is the long-term performance limit. All of these things last on the order of several years, which may not be long enough for the lifetime of your device. These materials will bake out and dry out. They'll just lose all solvent and become basically a solid and have very poor thermal performance, or they will pump out. And pump out is simply the liquid material leaving between the two plates and not being available for thermal management. The next is temperature limits. A lot of power devices have very high temperature limits, often over 125 C, over 150 C. We've seen some devices that go over 200 C. These high temperatures are not compatible with most of the thermal greases and phase change materials. There's also the installation issue. Most of the time, to effectively put on thermal grease, you need a dedicated clean room bay that does nothing but put on thermal grease. And you need a clean room because even a small bit of dirt, dust, grit, hair, anything is enough to have a bad thermal interface. The other issue with grease, it is famously messy. It's sticky, it's messy, it's hard to clean, and it's one of the real drawbacks, that the reason people don't use it. Now, installing grease is a 5-step process. We took this from an Infineon installation guide. You see the reference at the bottom. You'll clean your stencil. You'll put your stencil and align it on top of your device. You will screen print the grease. You'll remove the stencil, transfer the device to your heatsink. You will attach your device to the heatsink. This typically causes grease to come out of the bottom, and so you'll need to clean the grease that comes out. So as you can see, even in a clean room, it's a precise process. It's something that does need to be followed fairly exactly in order to get good results. We talked about the issue of pump out, and this is simply because greases and phase change materials are fluid, at least part of the time. And as you go through heating and cooling cycles and everything flexes and bends, this liquid material can escape from under the hot device. After several years, you'll see a device on a heatsink, and you'll see a ring of grease visible around the device. That is because the material has just pumped out over time. Once it leaves the system, it's no longer available to perform thermal management. How long does grease last, a thermal paste? We pulled this up from a website called connector.com, and this pretty much aligns with what we've heard from customers over the years. They expect thermal grease to last between 3 and 8 or 9 years, depending on the quality of the grease, how it's applied, the conditions it's applied in. And this is fine for a lot of applications. However, if you have an application that the expected lifetime of the device is longer than this, if it's 10, 15, 20, or in the case of an LED light bulb, 25 to 30 years, you want a thermal interface that lasts as long as the device. As part of these greases drying out during use, the power electronics industry has to compensate for the bake out and the pump out. And they do this by having preventive maintenance schedules. We were brought into the power electronics industry, and we developed a compressible TIM by one of the big power electronics users in Europe. They install motor control centers, many devices that use IGBTs. And these IGBTs, the grease on them was failing after a certain time period. Their solution to this was to develop cleaning kits consisting of a scraper, alcohol wipes, spatulas and additional grease, then they would send people out into the field with these cleaning kits. They would have to go to the motor control centers or the devices that use these IGBTs. They would have to shut the equipment down and then spend time disassembling, cleaning, and then reassembling all the components in the field. From what they said, these components were not always located in the cleanest spots. They were often in unused, seldom visited parts of factories and buildings. They were dusty, they were dirty. Due to the nature of the components, the area was often very hot. There would be fans blowing. And so it was often difficult to get good grease lay down on a field installation. They wanted something that was not going to ever wear out. And that's where we came in with our material. We do 3 different types of eGraph products. eGraph is just our name for electronics graphite. As a company, we do many types of graphite. These are the types of graphite used by the electronics industry. We have 2 versions of high therm, which is our name for thermal interface material with high Z direction thermal flow. And we also have a line that we won't be talking about today called spreader shield. These are heat spreading products that are designed to replace aluminum. They're thinner and lighter than aluminum. So we'll talk about the high therm products. Now, high therm interface materials have found usage in several areas in high volume. LED lights is probably our highest usage area for reasons we'll talk about, but also satellites, lasers, Peltier devices. An up and coming opportunity or application is electric vehicle converters. If you plug your electric vehicle into the wall, it's going to have a power conversion unit within the electric vehicle. They don't want the grease in there to wear out, and so they'll use high therm for that. And our other big usage area, IGBTs and power devices, and we'll mention those. Now, when would you use a graphite thermal interface over something else? Well, our high therm is ideal if one of them or more is true. Having a product with a long lifetime is important. And in this context, long lifetime is anything more than about 7 or 8 years. If you want something that's going to last without having to replace a grease, a paste, or a pad, then you would go with the graphite. Having a product that works at extreme temperatures is important. Again, some of the devices out there run at over 200 C, and which is no problem for the graphite. However, greases and phase change, it's pretty much at their limit. If you need a product with low outgassing, our products are just graphite. There's nothing else in there other than graphite. And so the material does not outgas. This is important for several different industries, and we'll talk a little bit about that when we talk about satellites and LEDs. And then having a product that is reworkable is important. Quite often, you have a module that you put on a heat sink. It would be ideal if you could have a thermal interface you could attach to your heat sink and then not have to replace it or rework it every time you switched out a module. And in that case, you can use graphite because graphite is very reworkable. Now, if none of those are true, then sure, use thermal grease, a phase change material, or a thermal pad. It would probably be acceptable for the project, and we would probably recommend you would use that. However, if any of the above are true, then we would recommend a graphite type product. Some of the product benefits of graphite, as we've talked about, it never wears out. The thermal conductivity of graphite is an intrinsic property of the material itself. Similarly, like copper has a very steady thermal conductivity, no matter how old it is. It's the same for graphite. You will always have the same thermal conductivity when you install it 10 years from now, 100 years from now. It is an intrinsic property. Tolerates working temperatures over 400 C without any change to the material or performance. In oxygen, you have to get over 420 C before the material will undergo any sort of physical change. In a reducing or oxygen-free environment, you can go up to around 2,800 degrees C before you will see any change to the material. This material is delivered as a foil or sheet form factor, so there's no dispensing equipment required, stenciling equipment, anything like that. You just place the solid material on the heatsink, put on the component, and then bolt it on, and you're good to go. We do have several module-specific die-cut parts already available. If you're using any of the standard IGBTs or power components, more than likely we will have a die already created that has that pattern already in it, correctly sized, and we can ship finished parts that look just like the picture there. And as such, it eliminates needing a separate dedicated clean room bay to install grease. And so you don't have the mess or the loss of a clean room bay because you use grease in there. All right, some of the places it's been used in the past. International Space Station, it was used to solve a problem on that. You'll see we're in a lot of satellite and space applications, and that is due to the fact that it does not lose any of its thermal properties depending on the pressure of the outside environment. The more you can be in a vacuum, you can be under very high pressure, the material will work the same, and the material will not outgas. Anytime you have a satellite, you don't want to have anything that's going to outgas anything that can coat a lens or a sensor. Hubble Space Telescope, we were on one of the repair missions for the Hubble Space Telescope for the same reasons. They wanted something that would not outgas. Outgassing next to a telescope would be catastrophic. And not sure how much longer the Hubble will last is a satellite, but you can be assured that the graphite will be functioning properly the entire time. Probably our largest usage area currently is in LED lighting, and it's for the reasons we've talked about. A good driver in LED system, like in an architectural type light, something a little more high end than you'd put in your living room, the lifetime of those drivers is in the range of 20 to 30 years. You do need a thermal interface that's going to last that entire time. If you use grease on it, it would dry out after a few years. You would have a thermal issue, and you would have a premature lifetime of your LED. So you first need something that's going to last the lifetime of the device. Second, you need to have something that will not outgas. The phosphorus coatings, the yellow part on the LED drivers, are extremely sensitive to absorbing chemicals. And if you have a pad or a grease that would emit fumes, it could affect the phosphorus, change the color, which would in turn change the color of the LED. And lastly, you see, a lot of LEDs are within bulbs. There's a glass lens over the LED. If you had something, a grease or a paste or something that outgassed, then you could coat the inside of that lens. And again, you would diminish the effectiveness of the LED. And really the up and coming area for us is in the power devices, IGBTs, inverters, rectifiers, things like that. Here you have high-powered devices. They can run very hot. They can have very long lifetimes. And you want something that will just work for the lifetime of the device. Several years ago, we had only one version of high therm, which was it's really basically non-compressible. The IGBT users came to us, one in particular, and said, due to the nature of IGBTs, you bolt them in the corners, and so you have a lifting in the middle of the device. And this low pressure lifted area of device makes it difficult to use a standard high therm. It makes it difficult to use grease, phase change, anything like that, because you have such a difference in height of the modules. And that was really the reason we developed the compressible TIM. And we'll talk about that a little more. Excerpts from our data sheet, these are available on the neograf.com website. We have two series of high therm, the 1200 series that is non-compressible, and by non-compressible, it compresses about 4% at 700 kilopascals. So it'll compress a little bit, but it won't compress a lot. And then we have the compressible material, starts off at 200 microns, and then compresses down. It can go down to about 30 microns, depending on the pressure you put on it. All of these materials, the more pressure you put on it, the better they work. These materials love pressure. There's no such thing as putting too much pressure on a graphite thermal interface materials. And if you have any questions on that, just let us know. We'll be glad to answer them. Now, we talked about the compressible material. So when would you use that? You use these in situations where you have two plates that are not completely parallel. This is the case of the IGBTs and many other power devices. It's just the nature of the device that the plates are not parallel, and you do need to make up for those low pressure areas. You have a minimum clamping pressure of 100 kilopascals. You need a long design lifetime. You can expect high temperatures, greater than 150 or 200, whatever you need. If you'll see harsh temperature cycles, if outgassing is not desirable, and if field servicing to replace dried out grease is not desirable. If you have those conditions, then that's a case of using the compressible material as opposed to the non-compressible. And for the compressible material, this is just a little schematic of what we typically see. The areas around the bolt holes, around the outside of the device, have high pressure. They're highly compressed, whereas the middle of the component board has lower pressure. It bows up, sometimes quite a lot. And you do need something that will compress around the bolt holes, yet have an expanded nature in the center of the board. And because the center of the board is really where most of the heat comes from. So you do need to have good contact right there in the center of the board. A question that we get all the time is on thermal conductivity of the material. When you're talking greases or thermal pads, they often advertise the performance in terms of thermal conductivity. For a solid material, thermal conductivity is a relatively meaningless number. if that weren't the case, a sheet of copper has a Z direction thermal conductivity of 400 watt per meter Kelvin. You would think it would make an outstanding thermal interface. But the reason no one uses copper for thermal interface is that the impedance is very, very high. So you always need to take a look at the thermal impedance versus the contact pressure you put on the material. And then you can decide if it's going to thermally meet your needs. So it's a much more accurate description of the material rather than just straight thermal conductivity. The red line, high therm 1200, the blue line is the high therm 2500 series. You see they have very similar performance. The green line is the compressible material. It starts off very thick and low density, and you do need to have at least a little bit of pressure to start to compress the material so it'll fill in the little micro gaps. And so you do need at least 100, 150, 200 kilopascals to really get it to start to perform well. And that's on the chart. And these charts are on the back of our data sheets too. A question we get all the time is, well, what is flexible graphite? And flexible graphite is just hundreds of thousands of graphite or graphene layers stacked up mechanically. A lot of people, and there's a lot of confusion between graphene and graphite. If you have up to about 20 or 30 graphene layers, just single layers of carbon atoms, then it's known as graphene. If you're between 20 and about 50 layers, it's sort of a transition area. And over about 50 to 100 layers of graphene, that's when it's officially graphite. And you'll see all sorts of definitions over there. But graphite is just stacks and stacks of graphene layers made in a practical form. A single graphene layer won't move a lot of heat. We also get a lot of questions about graphite. Is it used in industry? If you haven't heard of it before. And yeah, over the last 20 years, graphite's become the standard thermal management material in the electronics industry for all high-end electronics, cell phones, tablets, laptops, high-end televisions, LED lighting, set-top boxes. All of those use multiple pieces of graphite. It's the main reason why your phone today, even though it's so much more powerful than it was in the old Nokia brick days, why the phone is so much thinner and lighter. You no longer rely on a thick aluminum chassis to spread the heat. You now rely on a very thin, efficient piece of graphite. Same thing with your laptop, your tablet, all of those things. One of the reasons graphite has become so widely used in industry is because as a material, it's a very easy material to work with. Graphite's chemically inert to almost any substance. You need a very strong oxidizer, to the point really that if you expose your device to a chemical that would hurt the graphite, it would destroy your device far before it even touched the graphite. Things like fuming nitric acid, things like that can affect graphite. Graphite's completely non-flammable. It has the UL94V0 flammability rating. Since graphite is only layers of carbon, it contains no hazardous material. As such, it meets all the standards of RoHS, REACH, lead-free. It's a Sony green chemical. The waste is not hazardous. You can dispose of it in a trash can or a landfill. And it's very easy to cut and laminate with adhesives. It cuts just like paper. It bends just like paper. If you take a look at a piece of graphite, it's very flexible. It's very it's not very fragile. It's very good material. And lastly, one slide about us. We've been in the business for about 140 years. Most of our history, we were known as part of Union Carbide. We were known, a lot of you may know us as Graphtec. We were part of Graphtec for about 15 years. And for the last 5 or 6 years, we've been known as NeoGraf. But it's all the same people, the same factory, the same location in Ohio. The picture on the left was a drawing from about 1920, and the picture on the right was a drone photo they took just a couple of years ago. Same building, same everything. So that's what I have. I hope I've answered some of your questions about graphite thermal interface material, what it is, when to use it, when not to use it. And we look forward to any questions you might have.
Thank you very much, Bret, for this interesting presentation. This brings us to the question and answer session. You now have the opportunity to formulate your open questions in the chat. Please make active use of it. Bret, I would have 2 questions about graphite foils from my side. In which formats are the foils available? Are they cut to the needs of the customer or to the special IGBT? Which formats do you use?
Sure. Some of our material is made in roll format, some is made in sheet format. On the roll format material, if you use an adhesive on it, the material can be die cut to the specific size and shape of the IGBT or the power component. It can be presented on sheets with backing paper. It can be presented on a roll, so it can be indexed for either manual or automatic installation by the end customer. It really depends on the needs of the customer, whether or not they have automatic equipment to install this or whether they're doing it manually. We can present the material in whatever format works best for them.
Okay, thank you. And the second would be, are the graphite foils reusable, for example, in a repair situation?
Yeah. One of the nice things about graphite, especially the non-compressible material, it's reusable really as many times as you need it to be. As long as the upper plate, the part that's pushing against the graphite, is not sticky, it doesn't have any mechanical burrs or hooks in it. As long as the upper plate is smooth, you can compress it. Remove the plate, have a whole different module, install it, and that will not hurt the graphite in the least. We have some applications for our graphite thermal interface where the material is installed on the lid of a testing unit. You'll put a module in, close the lid, run it for a certain number of hours, lift the lid, put another module in, close the lid, and that continues for months. The graphite is extremely reusable, and it's one of the real advantages of it over a thermal grease.
Okay. We have 2 questions from our guests. First is from Tobias. Is there any information about electrical insulation of this material?
Sure. Graphite itself is electrically conductive. It's not a great electrical conductor, but it's good enough to consider it an electrical conductor. As such, you do need to be sensitive to that. Most of the highest usages of this product are, say, between the bottom of a module or the bottom of a metal core printed circuit board, where you have the bottom of metal is going to contact something that's metal. The bottom of the module can also be plastic, it can be ceramic, it can be really whatever you want. you just do have to be aware that you just can't have any circuitry exposed when you use this thermal interface. But it's the same thing as a grease. You're not going to expose circuitry to a grease for the same reason. So for applications where you cannot have something that's electrically conductive, then you wouldn't want to use a solid form of graphite like this.
Okay. Tobias have a second question. Is it also available for prime pack 2 and 3 and also in 62 millimeter housing?
Mm-hmm. Yes, it is available for all of the standard IGBT sizes. The only one that people have a problem with is the I think I want to call it the EconoPack Plus. It's 3 devices all put together, bolted down in the corners. That one lifts up quite a lot. We've had customers having to use upwards of 2 and 3 layers of material. But all the standard IGBT forms, there's die cut versions for those, and they're real standard, and they work really well.
Okay, thank you. Okay, thank you, Tobias, for these questions. He has also a third question. Is there also a material available that provides electrical insulation so that it is possible to reach double insulation?
Yeah, this material, you can always put plastic on the top. This material is a heat spreader, and you can see we've put a nice layer of dielectric plastic on the top, and that provides up to 2.8 kilovolts dielectric protection. However, plastic is also a good thermal insulator. And so if you have a very highly thermally conductive in the Z direction graphite, and you put a layer of plastic on it to prevent electrical shorting or to provide a double insulation, you have basically ruined the thermal transfer from the top to the bottom. You'll still get some, but you'll greatly diminish the effectiveness of the graphite. We do have a line of spreader shield products that we talked about that come standard with plastics, plastics and adhesives. Those are still fairly efficient transferring heat in the Z direction, and those come standard with plastics. And we do have customers, like in this situation, they want to transfer heat, but yet they also need a very high dielectric. And for some reason, some of the more commercial pads out there, like the sill pad, that is basically a piece of rubber that has some thermal properties, that's not working for them. We can sample some of our material that does provide electrical insulation. Just keep in mind, it's not going to be nearly as efficient as using bare graphite.
Okay, Tobias has a fourth question. Is it required by TÜV Süd? Okay, he explained why he asked this question. They want to have double insulation between module base plate and the heatsink.
Sure.
Thank you, Tobias, for this detailed question. I would say if it also have not answered 100%, please contact again myself or your experts at GVA and describe your detailed situation, and we get directly in contact with Bret to dig deeper into that issue.
I will say that is not an unusual question. All industries have asked us that, especially the LED industry, the power electronics industry. It's sort of a holy grail, if you will, within the industry to find something that's electrically insulative, yet very highly thermally conductive. Unfortunately, you can't have both at the same time. We've still found you can have high thermal conductivity, or you can have high electrical insulation. I know there's a lot of people working on something that has both properties. So far, I don't believe there's anything in the industry that really meets the need. You get one or the other.
Okay. So this brings us to the end of our webinar. If you still have any questions or maybe need samples of graphite foils for testing, please do not hesitate to contact me or my colleagues from sales directly. You will receive an email with the contact details of our responsible employees afterwards. As experts in power electronics, we at GVA have, of course, even more to offer than thermal interface material. In addition to the sale of a whole range of power electronic components, we develop and manufacture assemblies and systems entirely according to your specification, usually in the range of a few kV up to the megawatt range. Feel free to visit our website for more information. The best way to follow us is on LinkedIn. This is the fastest way to find out the latest news about GVA and its partners, as well as about our latest experts webinars. Bret Trimmer and I thank you for your interest. I would be happy to welcome you back at one of our next webinars. Take care, goodbye, and hopefully see you soon.